Hello geometry students, and welcome to lesson 7.4 on similarity in right triangles. In example 1, we are going to identify similar triangles that are formed by an altitude. So when you draw in an altitude to the hypotenuse, okay, meaning CD, of a right triangle, you create 3 right triangles. How are the triangles related? Okay, so let's take a look at this. If we separate the triangles, then the altitude divides ABC into 2 right triangles, okay, one on the left, one on the right. And if we take a look at these, we can see that because angle ADC, okay, is congruent to ACB, and angle A is congruent to itself, then we know that triangle ACD is congruent to triangle ABC. And that's by the AA theorem. If we look at the triangle on the right, again, we can prove that the 2 triangles are congruent by AA. So, triangle ACD and ACB are each similar to triangle ABC. We can also continue and talk about how ACD and triangle CBD are related. And since they are both similar to triangle ABC, they are similar to each other by the transitive property. Okay, so as we go through this section, I'm going to refer to the sides of the triangles. We've got 2 legs, which one is always going to be shorter than the other. So we're going to refer to them as short, long, and hypotenuse. Short, long, and hypotenuse. And short, long, and hypotenuse. So when we say short and long, we know we're referring to the legs. Theorem 7.4. So the altitude to the hypotenuse of a right triangle divides the triangle into 2 triangles that are similar to the original triangle and to each other. So find the missing lengths within right triangles. So given that triangle PQR is similar to QSR, what is the length of QS? Okay, first of all, I'm going to separate the 2 triangles. And this is a good idea. You may want to do this until you get used to visually separating them in your mind, if that's possible. If not, you can always just keep drawing them separately. So we can set up a proportion that QS, right, which is the long leg, corresponds to the long leg PQ. And that's equal to the same ratio as SR over QR. And then that will allow us to solve for QS by cross multiplying. And QS should equal 12. So, study tip. With right triangles, you can apply the Pythagorean theorem to verify your results. Okay, meaning, find the length of PR and then compare that ratio of PR or QR over PR to see if it's the same as the other ratios. So pause the video, try example 2, and find the length of PS. Okay, so hopefully you found that PS is equal to 16. Okay, as always, if you have any questions, you can ask about this in class. Example 3, relate the altitude and geometric mean. So this is a new type of mean, right? You're used to the arithmetic mean where you add 2 things and divide by 2, or add a number of things and divide by how many things you have. Geometric mean is different. And so you're going to learn about that now. So we're asked to figure out the length of CD. So notice that CD is the length of the longer leg of CDB, right, this triangle. 3.6 is the short, CD is the long. And it's also the length of the shorter leg of ADC. So again, this now would be the short, and 6.4 is the long. So we can set up a proportion. AD over CD is equal to CD over BD. Fill in the values. We end up with CD squared. Taking the square root, we get 4.8. So up here in the study tip, you can think about the geometric mean in another way. If x squared is equal to AB, then x is the geometric mean of A and B. So that's what geometric mean is. It's the square root of the product of two numbers. So in this case, CD is the geometric mean of AD and BD. So pause the video, try it for number 3, and find the length of CD. And come back when you're done. Okay, so hopefully you found that CD is equal to 5 root 3, and more often than not, we will be leaving our answers in radical form. Okay, this one was decimal form because the numbers given were decimals. So that's hopefully what you can go by for the future. That will always hold true. Corollary 1 to Theorem 7.4 says that the length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So when they're talking about the lengths of the segment of the hypotenuse, they're talking about BD and AD. Example 4, relate side lengths and geometric mean. So here we're given triangle RST, and we're asked what is the length of RT. So go ahead and pause the video, find the length of RT, and come back when you're done. Okay, and hopefully you read that study tip. Remember, if you're having trouble identifying the similar triangles and corresponding parts, remember that you can always draw them separately. So hopefully you found that RT is equal to 12. Again, if you have any questions about that, you can certainly ask in class. Okay, let's go on to try it number 4. You can try parts A and B, find the length of JL and KL, and then come back when you're done. Okay, so hopefully you got 4 root 6 for JL and 4 root 30 for KL. We have 2 additional examples for example 4. So go ahead and try both A and B. Pause the video and come back when you're done. Okay, for AD, hopefully you got 64. And for BD, hopefully you got 36. Please ask in class if you did not get these answers. Corollary 2 to Theorem 7.4. The altitude to the hypotenuse of a right triangle divides the hypotenuse so that the length of a given leg is the geometric mean of the length of the hypotenuse and the length of the segment of the hypotenuse that is adjacent to that leg. That's a mouthful. So what they're saying here is that AC is the geometric mean of the hypotenuse AB and the segment of the hypotenuse that's adjacent to the leg, meaning AC. So CB is the geometric mean of AB, the hypotenuse, and DB, the adjacent segment of the hypotenuse to this leg, CB. Now keep in mind, you don't have to memorize all this. I mean, this is exactly how it would work out if you set up your proportion just by matching up corresponding parts. So you can always, again, fall back on the idea of separating the two triangles, or doing what I had said, thinking about, short leg, long leg, short leg, long leg, short leg, long leg, okay, and hypotenuses, whatever it is that you need to use in your proportion. Okay, example 5. Use the geometric mean to solve problems. So now you're going to have some algebraic expressions. Okay, but just use what you've learned to this point. Try example 5 and both the triads A and B. Come back when you're all done and we'll compare solutions. Okay, for example 5, we can use the geometric mean that relates the two segments of the hypotenuse and then the altitude to the hypotenuse. So 6 is the geometric mean of x plus 5 and x. Here's the proportion. You end up with the quadratic. You have to move all your terms to one side. Okay, remember that, that's key. And then we can factor and find the solutions. And because this is an application involving length, we can rule out the -9, so the value of x is 4. -9 would not make sense as a length. For 5a, find the value of y. Hopefully you got 2 root 13. And for z, 3 root 13. Again, if you did not get these answers, please ask in class and we'll go over it. Example 6, apply geometric mean to find a distance. So we have a ramp, okay, a loading ramp that's 4 feet high. The length of the back of the base, so here's what they're calling the back of the base, must be 12.8 feet. How long must the entire base be? So go ahead and solve for that. And then you're also being asked how long should Zhang make the ramp. So you want that length of the ramp as well. So try both of these and then come back when you're done. Okay, so we can set up the proportion. 4 is the geometric mean of the back and the front. The back is unknown, or I'm sorry, we know that the back must be the 12.8, the front is the unknown, which we have to solve for in order to get the whole length of the base. So x is 1.25, and when we add that to the 12.8, we end up with 14.05 feet long. For triad number 6, the length of the ramp should be about 13.4 feet. So again, when the problems are involving decimals, then it's okay to give your answer in decimal form. Additional example 6, go ahead and give this a try. Come back when you're done and we'll compare solutions. Okay, let's see. So the length of BC. Here's the proportion. So CD is the geometric mean of 5 and 28.8. So we end up with CD equaling 12. And then we can use that along with Pythagorean theorem. And maybe you even recognize this triangle. We call it the 5, 12, 13. It's one of our Pythagorean triples. So BC's length is 13. So that concludes our lesson. Make sure that you read through the concept summary. Okay, there's a good overview there of everything we talked about in this section. I hope you enjoyed this lesson. Have a good day. I'll see you in class.